Hello, everybody. Good morning or good afternoon, depending upon where you may be. Welcome to our challenge 3. It's been a process, so um, applying GD&T, the GD&T rules. So, we thought it would be really nice to put this together, kind of stepping through um, in accordance with ASBY 14.5, dimension and tolerancing. So I had this little assembly design we call the well flange assembly we've been dealing with. Um, we had done 2 prior challenges, challenge 1, challenge 2, and challenge 3 now was still dealing with the same mechanical joint and taking a look at that. And basically what the whole thing was about is no matter what your product is, no matter what you're doing, it's got to do something. In other words, you have system requirements of what your product has to do to meet the intent that your customers are going to purchase a product. I've seen so many times in industry working with so many different engineering teams that sometimes it's easy to get tunnel vision. Um, um, and doing things. Are you applying the rules? Are you in the plus minus world? Are you in the GD&T world? So here we're just trying to do concepts based on the ASBY 14.5 standard and some of the tools that are in the standard that can help answer or prove out mathematically your design intent. So the one thing engineering must be doing, asking the right questions about what's going on with their product. So here is challenge 3. Let me go over the high level here of what we were talking about based on challenge 3. So again, what are we looking at? We're just looking at the same challenge that we have been for the previous 2. It's an assembly of 2 components, a male and female component coming together. It's called a well flange assembly, where they'll be added on to at a next level structure, but it was about the mechanical joint, the interface between these components here. So what I have is I have the weld male flange that's going to fit into the female flange over here, and there are key interfaces that pulls them together and a sealing surface. Now I simplified this compared to the original. I left some parts off. There's actually a seal that would be in here. I removed that for simplicity of just talking about certain elements that engineering would utilize at making an evaluation of a mechanical joint. I have hardware going in here, and here what we're using is quarter 20 hex cap screws. And it's really about this right here, that you're bringing together 3 components and they all have to play together. Sometimes engineering, they'll just focus on the individual feature, the hole, the tapped hole. And oh, by the way, there's a bolt. But if you apply GD&T correctly, you'll look at this as what I call a collection. They all got to come together. I can't tell you how many times I've heard, I can't get the bolt in the hole, or you cross thread down here when you put the bolt in, because we didn't do the due diligence in engineering to prove out mathematically this would go together if the parts were compliant to the engineering drawings. Now I've had parts come in compliant to the drawings, but since we didn't do the due diligence, didn't ask the right questions, it wouldn't assemble. So that's kind of just the overall, all these exercises what we're doing here. So the requirements was, the assumptions is that here dealing with these was dimension and tolerance was based on the ASBY 14.5 dimension and tolerancing standard. The components were in inch-based rules. Here again, 14.5, you can do it in either metric, millimeters, and or inches. And the only differences between the two, there are unique rules to apply, whether it is inch-based dimensioning or millimeter dimensioning. But that really is not impacting here. It's about some of the other philosophies here about proving out the joint will come together. So here, this on the 3rd challenge was dealing with the same joint, with the same design intent and dimensioning scheme. And one thing here, the fasteners were not key locators. They were just really, the intent was clamping the two parts to hold the assembly together. So they weren't key locators in this case. What the key locators here was mating on these primary planes, and then both the pilot diameter fitting into the hole with the true key locators in this case. And the bolts just held the joint together. So the takeaway here for this challenge was using the solution we provided, dealing with challenge number 2. And this is what we're asking you to do down here, is that based on this call out now, it's that determine how large can the clearance hole could be made. I've seen in engineering what they'll do is they'll just automatically maybe default to either drawing block tolerance or maybe just the drill size, depending upon the tool that's going to produce the hole. So my question here is that, if it's only a clamping force, why do we have to hold the hole so tight? The main thing here in this joint, holes don't interfere with the bolt going in the hole, and the bolt's going to just be a clamping force. So do they really have to be tightly toleranced? So that's my question here. What changes would be needed to give more tolerance in manufacturing to the parts? In other words, how big can the hole really be? And we'll be taking a look at that, and some of the things the hole cannot protrude out. So here was the main takeaway. The hole cannot protrude out from under the head of the bolt. So that was definitely the one thing I kind of alluded to, is that the hole, wherever it goes, will never come out. And then I also stated that, oh, by the way, you can't make any changes. So the hardware is going to still be the same size that we showed you in the previous slide. No modifications to the tapped hole side of the part. And by the way, I try to allude it to make it a little bit more definitive here. The 281, you can't change the 281. So I was trying to limit it to some level of degree. But I got to admit, some of the responses I got, they were kind of creative and wound up doing some items here to get the same evaluation or collective effect that what we're looking for here. So it's basically, we're looking still on the clearance hole size. So just to break the requirements down, the goal was, how large could the clearance hole be made? The hole cannot protrude out from underneath the head of the bolt. And then again, you can't change the hardware size, can't change the tapped hole, and you can't mess with the nominal diameter, 281. And then there's some assumptions here also. Oh, by the way, we're going to assume that there's no positional error between the head, the hex bolt head, relative to the threaded feature. Just no consideration of that, in other words, they're perfectly coaxial, no positional movement. So what we're looking at here is dealing with this clearance hole, but now what's fitting in that hole, we're going to look at the fastener. So looking at this here, I didn't change this. I left this in all 3 cases. And after looking at this, I maybe for challenge 3, maybe should have been a little bit more descriptive, but no value. I did make a comment here. So what we said with this bolt here, that use the nominal or basic fastener values if values are needed from the table, which we provided, shown in the table as basic values. And then here, oh, by the way, do 3 significant digits. Okay, so again, focused here, but you're going to have to look at the hardware. So I actually calculated out there could be 3 possible answers to this here, depending upon what values of the hardware did you use to derive your answers. Okay, so I'll step through those. So the thing is here, calculating the largest hole. So really, how large can the hole be? So we're focusing on, what are we talking about? That right there, that value. Again, I alluded to that, some people, well, the process is going to do this, can hold it really accurate. Yeah, that's based on maybe process capability, but design intent wise, do I have to hold that tight? Can it be larger? And if it can be larger, well, how large can it be? And that might be some design intent issues that you might have to address. And what we're going to be looking at is the head contact area relative mating against this flange. That might be some design requirements, area contact, loading, torque. So there's a whole plethora of other requirements possible that might determine how large that hole could be. So I didn't really address those. I just asked how big could it be without going underneath the head. So that was the only requirement I put, negating any of the other design requirements, loading, torquing, things like that, that you may have another design requirement that you might have to evaluate. So again, the takeaway, the hole cannot protrude out from underneath the head of the bolt. That was my only requirement based on that. And then these other requirements here. So some of you may have seen this. This here has been around a little bit in industry. I've implemented at some of the companies I've been at and shown to my engineering team. And really it's this right here, is that in this case here, whatever size fastener you are using, think of it this way, push the bolt all the way to one side of the clearance hole. Then the requirement is that whatever that size is, that clearance hole will never come out from underneath the type of head you're doing here. So what we're worried about here, being a hex bolt, the minimum distance would be across the flats, not across corners. So the requirement is the max hole gives no exposure underneath the head of the bolt. So in this case here, it would be across the flats would be the minimal distance here. So if you actually do this, take the fastener body, and then determine what the areas of the head relative to the body, well, that's the largest that hole can be, the LMC size of the hole. I've actually had people ask me, well, Ed, I don't even know what to do with the hole. How small, how big? And I said, well, it's design intent, but you could use this rule here as compared to just either using the drawing block tolerance, default plus 5 thou, or tooling size. Jim, I mean, if you actually really take a look at the ASME standard on drill sizes, you're going to see the drill size are held pretty tight for the actual tool. Now, when the tool is placed in a machining center or process, well, there's some variation that kicks in with the tool head, the machining, repeatability of machining bed. But here we're showing you there is a standard that you can calculate, or a method, I should say, not a standard. So here to derive the LMC size of the hole, you could take, in this case here, being a hex bolt, take the width across the flats, add the fastener body diameter together, and derive that by 2, and that will give you the hole at LMC. Now, what values to use is the question mark here, and I'm going to show you. I went through 3 different methods. My methods here is that, in the case here in the hardware, I said, well, use the basic values. So you would use the basic values for the width, basic value for the body, and you're going to derive a particular LMC size. But if you really want to know worst case, well, you would take the width across the flats at its LMC size, and then the fastener at its smallest diameter. That's another method I show. And then I do a combination that if you leave the fastener at its nominal, 250, and then use the LMC, there's a third variation I did. So I'll show you all those could be what the values are, and that's what we'll step through today. So here, based on method 1, basic, if you use just the basic values like the requirements I had, per the challenge. Well, here is an example of one of the standards controlling this type of hardware. So the first thing is, well, what size is the bolt? And here, as I said, well, in this case here, use the basic diameter. So in this case here on this chart, the basic for the bolt would be, in this case, 250. So that's what they're alluding to here, nominal size of basic value. Now, there is tolerance on these bolts, but right now I was saying if you use the basic, use these. So in this case here, the fastener diameter, the nominal value or the basic value would be 250. So that would be the fastener size. Then we can come in and look at, okay, what is the dimension for across the flats? In this case here, again, the basic value, basic. Looking at this chart, you can see that it's back in the fractional world, 7/16. There is a max here. In this case here, and also if you did take this out to the significant digits based on 7/16, the ASME 14.5 does have a rounding rule to round that up. It's called, the standard we point to in the 14.5 standard is IEEE ASTM SI10. And they have a unique rounding method. So in this rounding method here, they would round up to 0.438 for the 7/16. So in this case here, the width across the flats for a basic value would be this value. So we derived the two values for the basic bolt, the basic across the flats. Now we can populate that into the equation. This case here, using that equation I showed you about shoving the bolt all the way over to one side of the hole, and now we're going to run the numbers of what the actual hole at LMC size would be, the largest. So here, the basic width across the flats, 0.438, we're going to add it together with the basic diameter, 250, and then divide by 2. So in this case here, the largest hole would be a hole at LMC, 0.344, based on basic values. So now if I come over here, what are we talking about? Well, we have this new derived hole at LMC, and we're talking about that's the upper limit, the biggest the hole can be, and what we're talking about is the upper tolerance. So now we can make the assessment based on the hole at LMC, how big could that tolerance be? Well, just a little bit of math here. Take the actual hole at LMC minus the nominal value, the 281. I said, leave the 281 as is, don't mess with it. Now I can extrapolate what the plus size would be. In this case here, my new upper limit size tolerance would be plus 63 thousandths. So that would be the new value in this case. Meeting that requirement, don't let the hole come out from underneath the head of the bolt based on basic values. So now with this new revised here, how many drill sizes can now be utilizing in meeting the drawing requirements? Well, I have a producibility book that I use, one of them, one of many I have. So right now, if I extrapolate based on the way the dimension is, so I have my nominal 281, I have my lower limit, smallest hole, the MMC size, and then I have my upper limit, or the hole's LMC size, and we just extrapolated them. So the smallest the hole will ever be, 265, and the largest will ever be 344. Now, if I compare that, you'll see that meeting based on producibility of that particular drill, the hole could come in as they use an H drill, would meet the requirement 265. Then how big could manufacturing do? Well, if you see here, taking based on producibility, and then if you round this up, it definitely would be compliant. Now, if they did try to bump it up, again, I look at the extreme values that if they did use an R drill in this case, based on producibility, they might exceed the drawing requirements here, in other words, larger. So again, this would be a manufacturing decision. That's a limit I have based on the engineering drawing. The manufacturing engineers, will be based. Would they be up in this limit? Probably not, right? But what I'm trying to allude to is, look at the amount of tools that I've just now allowed based on this drawing. So the exercise challenge 3, how big can the hole be? And the requirement I stated was as long as the hole didn't come out from underneath the head. Now, if I make the comparison now, based on this, the original call out we had was this, minus 16 thousandths plus 7 thousandths. And that 7 thousandths was based on a 281 tool, and that's what you could typically expect based on that drill size for producibility. In other words, over here is what we did. So this call out, when we did it, when we dropped it down to 0, if you remember originally it wasn't here. We had 15 thou, and this was really tight, and manufacturing could only use the K drill to produce that hole. Then when we asked a question about applying zero tolerancing, well, how small the hole could be, we went from 1 drill size up to these 4 drill sizes by applying this concept, 0 at MMC. And now we allow manufacturing 4 drill sizes for allowing how small the hole could act. Now we went the other way, asking, well, how big? In this case here, based on this case, this comparison, now let's look at a producibility of drill sizes. So now here, these are now all accessible based on this call out. Which call out would you want? So again, like I said earlier, this was only a clamping, the bolt was just clamping. Clearance hole do not interfere with the bolt. Based on some design intent, some questions we were asking. It's kind of funny, my dear friend of mine that's at the company I was with, he struggles. It's like, man, Ed, I've been doing this so many years, this just doesn't seem good to me. I'm like, well, I just, so if they do make the hole bigger, and if it meets the design intent, why don't we allow manufacturing all these drills as compared to 4 drills or 1 drill? And that's really all I was asking here. This exercise is just engineering to open up, do the due diligence, and allow as much variation on the features as possible without compromising design intent. That's really all these exercises are about. Engineering, ask the right questions based on each individual feature on your part, and give manufacturing as much tolerance as possible based on design intent. It's so easy to do a design and make every feature tightly toleranced. Well, you're gonna drive the cost up. And I've heard well, Ed, the process we're gonna do, it's capable. Fine, that's capable. There's other things that make a part non-compliant. Inherent stress buildup, distortion, other things can play in here. Myself, if you look at a lot of my designs, you'll see a lot of zeros and you may see a lot of this. I'm giving manufacturing everything possible to provide me a part that will go together. So that was method 1 using basic values. Now I want to calculate a new method here. What happens if we look at the actual extreme values here and didn't take the basic values? So now we're going to start looking at there, instead of being basic values, we're going to look at the LMC condition of the features. So that could be another assessment. Now, some companies I was at, we already had guides in when to do what methods, or some companies already have a predefined what your holes may produce and what they want to see in your engineering drawings. Last company I was at, I provided that. I provided them a complete guide dealing with what should holes be in sheet metal based on punching processes and allow manufacturing most tolerances. And I also took, based on drill sizes, and believe it or not, ASME has a standard on clearance hole size. I did a whole chart for them based on a loose fit, close fit, or what they call a normal fit. And I did a whole cheat sheet for them. They could actually look and derive all these. So I was just showing engineering that there's more than one way than using the crutch or the plus minus default tolerance or holding very tight tolerance. Now, if the hole's a key locator, yeah, you may want it really tight. So, but I'm just going the other way. So now the extreme values here. So originally, remember we used for the fastener size, we just left it its basic, and it was a quarter 20 bolt. Well, now we got to derive, well, what could be the smallest bolt, the LMC size? Now we're going to have to go off and check some standards out. So again, remember what the call out was for the tapped hole. Well, in this case here, the bolt is going to be a quarter 20 bolt. I went over to the ASME standards that controls these types of features and pulled that standard out. So the ASME B1.1 is dealing with screw threads for inch. Okay, they also have metric, that's ASME B1.13 that does millimeter hardware. So in this case here, you can see that we're going to focus on this right here. So I just pulled out about quarters. And if I blow this up, so you can actually see you have class fits. So notice we got a 2B up here. What are we going to come down here is going to be dealing with the 2A. And lo and behold, there is a possible minimum requirement the major diameter could come in at. So looking at, again, remember I said 3 significant digits. So in this case here, the LMC in this case, I would round it up to be 241. So that would be my LMC size for the actual major diameter of the bolt. Now, going back to the chart dealing with the bolt, now we're going to focus back onto the across the flats. And if you take a look here now, what's the LMC size for across the flats? Well, in this case here, that's the min, or 0.428 would be the LMC size across the flats. And again, we're assuming that the head of the bolt is perfectly coaxial to the axis of the fastener. You'll see all these little notes up here. They are talking that typically that could happen, but we're ignoring those. Those would be items you may have to address if you're doing this, but I put in my notes up there, make the assumption the bolt comes in, the head is perfectly in line with the body. So again, now we're going to derive the new hole at LMC. You're going to take the LMC across the width of the flats, and then we're going to take the LMC of the fastener. This would probably be probably your worst case scenario that you could do. So in this case here, I came out with 4 decimal places, and using the SI10 rounding rule, this case here, the 5 would just drop off, and my 3 significant digits would be 0.334. So based on SI10, this would not roll up to 335 based on the rounding rules, just FYI. So that's how we get to now 3 significant digits. I'm going to use 0.334. So my new value is here. It's going to be tied to this. And again, step through, taking the new value, 334, minus the nominal, 281, I get a new upper limit, and 0.053. So now this changes based on if you're going to do the extreme values method. So you can see here we get a little bit smaller, not allowing the hole to be as big. You're being a little bit more conservative. So again, these are decisions engineers would be making. I have made these decisions myself in going through this. So that's why I just want to show you your options. So now with that being said, how many drill sizes? So we can now make a comparison to producibility based on our new value here for how big the hole could be, size only, compare it to the producibility chart. In this case here, the lower limit didn't change to 265. Now the assessment here, it looks like for us to meet the requirement not to exceed 334, it looks like now we went down to the biggest we can be is a P drill here. If we try to go up to the next level drill, there could be a possibility it could exceed the requirements here. Again, that would be a decision that I state on my drawing, here's my limits. That's something a manufacturing engineer might be doing. Would they want to be all the way up on this end? Probably not. Probably not. But you can see again, we still are going to give them a lot more variation compared to the, remember what this was? Plus 7 thou. Plus 7 thou. And it would really tie their hands, the manufacturing engineers' hands, of how many options they have to make the part or try to get the part compliant. Same thing, the original call out was this. Now based on this method 2, using extreme values, that's still 4 drills. Now with being a little bit more conservative here, that we drop down to now 12 drill sizes, as big as we can do as P. Same thing, this or this. And method 3 here is a little bit kind of a modified basic fastener and then using the LMC. So this is the third one here. So same thing. So for this value here, they will use the 250 basic, but they're going to use the LMC here. So it's just a slight modification. So I'll step through this here. So in this case here, they did wind up using, so they are going to use the 250 for the bolt. And let me speak to that. If you use the 250 for the bolt, you know the bolt is going to come in smaller. The only time the bolt may come in at 250 if it was a class 3 fit. But what winds up happening here, if you use the 250, you're actually adding a little fudge in there, or if the bolt bends a little bit, it's not perfectly a cylinder. There's the right median line, it's bowing a little bit out of straightness. So it's just another way maybe to add in a little cushion that if the bolt didn't come in perfectly straight. So again, these are decisions. So we're going to use the LMC across the flats. In this case here, for the actual diameter, we'll use the basic value, 250. That's going to now derive me an LMC of 339. So again, what are we talking about? How big can we make the plus side of this here? If we do the 339, do the math, my new upper limit becomes at 0.058 and readjust it from plus 7 thou up to plus 58 thousandths thou. Same thing, stepping through this. Again, this winds up getting here, in this case here, doing the same thing, doing the comparison. So it's really about this, all these challenges were about was really asking the right questions, not compromising design intent. There are tools in the GD&T toolbox, in other words, in the dimensioning tolerance standards, we have assigned formulas. You can calculate what we call boundaries. We have inner boundaries, outer boundaries, depending upon an internal feature. How small can a hole act? How big? If you're dealing with shafts, well, how big can a shaft be? How small? You can derive and calculate all these boundaries in this case here. And here, I just left it here. somebody was creative and came in here and actually converted it from what we call a directly tolerance, and they actually made the value here basic 281, and they redistributed this tolerance into an unequal bilateral profile. And in that case there, their results gave me the same effect of what we're stepping through here in position. So you can see that sometimes that what are you concerned about isn't an axis control, then maybe you want position. In this case here, what we're worried about was the hole's boundaries. In that case here, then making this basic and using surface profile is applicable. You're protecting the boundaries. I didn't talk to that or add it. I didn't have it in my slides, but somebody did that. Kudos, that was pretty good. I like that. So there's more than one way. So all these exercises here was, first challenge was, oh, are you aware there are standardized formulas that we have in the ASB 14.5 that if you wind up utilizing these formulas, you're going to look at this whole collective joint collectively, not individually. You'll have individual contributors like the tapped hole, the clearance hole, and then when I thread the bolt in based on whatever this threaded hole's doing, collectively, what's the bolt going to act like? That formula handles that. And if you utilize these formulas, you can prove out mathematically, will the parts go together if the part's made compliant? So these exercises are about, are you familiar with the standard? We do have some standard tools in that toolbox that can help you prove out your design is solid and if parts are compliant will be true. Now there's a lot of other things involved. I kept it simplistic, you know, how the datum features act. I didn't bring in datum shift, but that's another element that may be involved. But I will say this, notice that the holes are always basic. The tolerance zones we're talking about are locked in those basics. Datum shift is not additional tolerance. In this case here, dealing with these features, the shift itself, datum shift, and the mating relationship between the bolts and the holes are based on the positional tolerance. And I really don't, you know, that's definitely way beyond the scope I want to talk to for these challenges. So here, challenge one was really, we stepped through, everybody did a pretty good job picking out based on the datum structure. And then if you use the positional tolerance and you got the values that were in the feature control frame, hence this, and now you proved out mathematically if the parts are coming in. Worst case here, you might get a point-on-point or a line contact element, but that was if both parts go to extremes. Yeah, that could happen. What's the probability? I can tell you I've done this thousands of times and usually it hasn't come back to haunt me, FYIs. So challenge one, position formulas. Challenge two is about the application of zero tolerancing. In other words, in this case here, how small can the hole act? And again, that was based on what we call the virtual condition or the inner boundary, based on that collective effect of geometric tolerance at 15 thousandths and the hole at MMC, how small could it act? And we said, well, if the hole could act as small as 265, why don't we readjust these limits to allow manufacturing to take advantage of additional tolerance? So that was challenge two. And that's what got us over to here. So in this case here, we had 15 thou here, drove it down to zero. That 15 down, we readjusted the lower limit, and then it allowed us more drill sizes here possible for manufacturing based on this here. This challenge was like, again, design intent driven. How large can I make the holes? And then what we're focused on was just this value right here. How big? And that's really what it was all about, is asking the right questions, doing the due diligence, And there's a lot of tools in the GD&T toolbox, or I should say the 14.5 dimensioning tolerancing, that you can prove out mathematically to control these boundaries of the collective effect. And with all these features on this part, there's going to be two boundaries. There could be a size and then a collective effect of location with the size. And that's pretty much all I was trying to get across in all these exercises. I have gotten a lot of responses doing about producibility and all that. That's much more. There's much more you can get involved, dealing with producibilities, statistical probabilities and things like that. But really, it's just pretty simple. How small can the hole be? How big can it be? And can you prove out mathematically if the parts are compliant, it will go together. And that's pretty much it. So, questions, concerns, answers. Or let me say this. Have you seen this before? Oh, let me get to the right slide. I had the opportunity, being at the ASME meeting, we actually had a major automotive manufacturer come and present to the 14.5 committee talking about this very subject. And they use this practice. When they looked at a vehicle, they made the assessment 85% of the holes that were in the vehicle, all the fastener was doing was a clamping force, not a key locator. And they questioned themselves, how come we're using like the drawing block tolerance, plus or minus 5 thousandths on the holes? And when they looked at all the holes they're putting in that were 2 plus or minus 5, it's like, why are we doing this? We have some parts that are coming in non-compliant. Can we open the tolerance up? And they actually came and presented this to ASME. And they were asking us, hey, can you put this in the book? And the committee is like, well, it's already in the book, not in this fashion, but we have the positional tolerances and these other rules. So I don't know. I don't know if this helps. Again, it's a guide. Or is there a design intent of area contact between the head and the mating part? That might be another design requirement. So again, questions, concerns?
Jasper, I have unmuted you. If you have a question, go ahead and ask it.
Good morning, guys. Thank you very much for bringing this up. And I have a little bit deviated question from the topic, which I noticed on the examples used, and would like to get some better understanding on that. The tolerances used on your examples are asymmetric. Do they have any benefit of having asymmetric tolerances, or from the process point of view, using a symmetric tolerance would be better?
That's a good question. I was trying to minimize all the possible solutions here, so that's why I kind of put a stake in the ground about leave it at 281, but do you have to leave it at 281? No, and that might not be to where, could you do an equal bilateral? And if you only worry about the boundaries, could I come back in on this drawing here? Let me get to one of the drawings here that shows the, so could we have readjusted this, that this value here possibly became the actual mean and then did an equal bilateral tolerance? Yeah, you could do that. You could do that. I just try to minimize all the possible answers I could get. So that's why I put a stake in the ground and say, hey, don't mess with the nominal here, but could you? Sure can. So it was just my way to minimize as much input I could get. So if you could, as long as you meet these boundaries, right? And the standard does give you a variety of different options here that you could do in what we call an equal bilateral, and this, the nominal value is mean, or you can do a unilateral. I could have drove this all the way down to the lower limit, make this 0, and then give all the plus up here, as long as they all give me this answer here. But now, I've seen sometimes in here more with tooling designs, or my tooling fixturing people, they'll sometimes lead to, they're doing what we call unilateral. They're leaning more one way, they would prefer to see a part. So again, that's a design intent, but to answer your question, no, this could have, you could have easily done an equal bilateral here. I just said, no, don't do it for this case, just to keep the answers at a minimal.
Thank you. Thanks.
Mm-hmm.
Okay, Ed, I have someone typed in a question. Why on method number 2, the position error between the head of the bolt and the head of the body is not taken into consideration? I have noticed that only 0.241 diameter is used. We know that the bolt is centering on the pitch diameter and not on the major diameter, which is the value used.
Yeah, I mean, if you really, I mean, I could have made this a real science project, because you'll see on this, like on this here, which I didn't put, oh, come on, I'm trying to get my laser pointer to work here. There is requirements here. In other words, I was making the assumption not to take all these in consideration. You may have to when you really do it. So I was trying to keep it a little bit more simple and not go into a more complex type application. Have I had to do this? Absolutely. That I would have to then come in, because look up here, there is a position tolerance up here. That, yeah, the head relative to deriving off a datum axis A, which is over here, yeah, in that case here, then you would have to take in consideration, so these values could get, definitely the values I derive might allow the hole to pop out, because in that case here, if the hex did shift more one way, then the hole may pop under. So I try to keep it simple and not go into this complex here. But now again, I just want to point out, I didn't show you the standard where this come from. You can see this standard for this particular hardware definitely gone to depths. But if you were, let's say, a design activity group and you're buying McMaster hardware, good luck. McMaster hardware is just selling hardware. It'll be lucky if they actually point you in the direction of a standard that goes this deep in what a actual hardware. Myself being in aerospace, we had to worry about this because hardware was critical. So hopefully that helps. You would have to consider it, absolutely.
That's great. Thanks, Ed. Michael Kozlowski?
Yeah, hello?
Go ahead.
Yeah, my question is on the tolerance block of the threaded feature. You don't use maximum for the positional tolerance, although the standard does use it. So what is the convention? What is correct?
Okay,
you know what
Michael.
I mean?
So you were saying, so could you say that one more time?
If you open your drawing slide with the any of the number 1 or 2 or 3 on the you see if you have positional tolerance for the threaded hole, it's for the female, for the other part, for the mating part, where we have threaded holes.
So
not for the male, for the female, yeah. Female flange. Yeah, if you take a look at 250-20 thread tolerance block, you have positional tolerance I believe it's on the next slide again. You see, you have 0.015 and then projected tolerance. You don't have M, although standard shows M. If you take a look at ASME Y14.5 standard, it does provide maximum material for the threaded features. So my question is, what is correct? You know.
Oh, and that's an excellent question. The standard ASME Y14.5 does show an M in here.
Yeah.
But now, dealing with threads, that it's a helical type geometry that you're dealing with, V shape. When you put the bolt in here, the bolt is going to self-center. So some companies, can you put an M modifier here on a thread? Absolutely, standard allows it. Do you get the M concept is about the feature departing from its MMC up to LMC, that as the hole gets bigger, I can allow it to move more. The downside about threads is that since it's a V-type geometry, as I torque the fastener, it will self-center the bolt to the threaded hole. So it's not like you do get that additional tolerance. The bolt will shift all one way unless you forcibly hold it up against there. Have I used them on my threads? Yeah, not so much for the additional tolerance. Once I do M's on threads, I can do gauging. In other words, I can literally build a gauge. But to answer your question here, I left it off on purpose. In this case here, try not to focus, because that in itself could be a debate. Some people say you should, you shouldn't. I say it's okay.
Yeah.
That you can apply.
Exactly. This debate going on and on and on, and we have to come up with some rule whether we use it or not, because otherwise it's an ambiguity, I believe.
So
yeah. And also, you know, yeah, go ahead. Yeah.
So would you put an M on threads yourself?
Well, I would, because the standard shows M, and you know, again, it's debatable. But if you follow the standard, at least you have a document that you can rely on, or you can, you know, refer to. Otherwise, you know, it's just because your personal preference doesn't mean that you follow the standard.
Right. Again. And again, I personally like M's on threads. Not so much I get the additional tolerance that threading could be out of position. And if you really did look at the thread size, like for example, if I hop back over to, where's my little, right over here. So you'll notice dealing with the bolt. The bolt does have size variation for the major diameter.
Yeah, exactly. Because it's a feature of size, you know.
Right. And now this is the bolt, but then the bolt's fitting in a threaded internal thread, and depending upon the class fit, that's the slop. But again, once those two features you start torquing them, they'll try to self-center. So it's not so much you get the additional. I personally like M on threads because I can build a hard gauge to check that when you have M's. If I don't have the M on there, I have to have an expanding gauge element that would have hit on the pitch diameter of the thread. And I've done that too. I've had flight critical hardware keeping things flying in the air. We were very critical of threads, and then we were not using M's, and we'd actually come off the pitch diameter. And typically they were class 3, so they were very tight fitting hardware, that there was minimal shift between the internal external features. But then that's, again, what am I talking about? Design intent. But yeah, good point. I like it. You can use them on threads. The standard does allow it. Absolutely. That's a good question.
Another quick question. You know, when in my company they see zero at maximum material conditions, they just, they don't understand it, and they don't allow. I don't know how to deal with this, how to explain to people, but when they see it, it's impossible,
Oh,
yeah.
They must be jumping out of their seats.
Yeah,
Right,
I mean,
exactly.
yeah, I mean, exactly. If they just look at this, and I've had it happen because I've done part myself, where maybe we had a value in here, 20 thousandths. Then all of a sudden I did zero. They think, oh my God, Ed wants a perfect part. No.
Yeah.
That tells me right away they never knew what this M meant.
Yeah, but it's very hard to persuade people. At least it's not my ability, not within my course.
It is, and I've had to do that numerous times myself, and go out to suppliers and actually teach them what zero at M really means. Where does the tolerance come from?
It gives you
right here.
It gives you more freedom, not less, But correct? Zero gives you more tolerance.
Yeah, you're
zero
allowing
maximum. Yeah.
Right, you're allowing them to go all the way down. If they choose to go all the way down, now they're going to have to be really, if they do make the hole, in this case at MMC, it will have to be really accurately located. Yeah, you're right. So don't make the hole at the 265 size. You can make it a little bit bigger. And now my manufacturing engineer, if he knows this, he can come up here. Look at the size of this hole, what we did here. Remember, originally it was like, what was it? -1 plus 7,000. So we only had a total of 8. Look at this. This is like, huge. I can do this with a hand drill now compared to.
Yeah.
So again.
And also, yeah.
So go ahead.
Yeah, but it's hard to persuade people again. If they see zero, they just think that I'm crazy. How come you demand that we made it perfect? It's impossible. Give us some tolerance. They don't understand. And also talking about the previous question, I would rather put both, upper and lower limit in diameter. In this case, you see your maximum and least material condition right away. You don't have to calculate it. But it's my preference.
Now,
instead of 281 plus 7 minus 16, you can put 250, whatever, two different levels, and you will see least and maximum material condition right away. Correct?
Right. So like, to help support what you're trying to do here, here's what I usually do. I'll show them this and show them, well, here's what this translates into manufacturing wise. Yeah. Then I do this.
Right.
I mean, look at this. It's quite obvious.
Yeah.
I mean, this is kind of hard to see it up here. I usually do this comparison. I mean, how can they say, what I just did here? I gave them much more tolerance here compared to what this, but for some reason, the suppliers like this, but I'm holding
I know, yeah. This is exactly what I was talking about. And when the machinist sees this zero, he just gets crazy,
Oh yeah, they freak out. They're like, oh my God.
Yes. So I believe we have to promote knowledge, otherwise people they don't understand the language of this standard. And overall, when they see too many different callouts in GD&T, they think that the part would be much more costly.
Oh, absolutely.
Yeah. When they see plus minus in the title block and less amount of information on the drawing, they think that the part would be much less costly.
Yeah,
yeah.
Exactly. Like this part over here, they would charge me $100 for this part. When we revise the drawing and do this part over here now it costs $400 instead of $100.
Yeah.
Because they seen this. Yeah. They didn't realize, no, look what I did.
This is paradoxical, but it's a reality. So if you do use this tolerance per this standard and provide drawings full of this science, you know, some of them will raise the price rather than lower the price of the cost.
Exactly,
You know?
exactly.
But
So
it's bad, you know, what to do with it.
Exactly,
Ed,
exactly. Yes.
I have another question pertaining to zero at MMC.
Okay.
Will zero tolerancing encourage manufacturing to run holes larger and thereby not centering the process?
Well, what winds up happening if you're allowing this here, and you have a knowledgeable manufacturing engineer, what winds up happening here now, where, for example, over here, you know, if they center the process, maybe the process they'll shoot for this size here, if they're trying to minimize the risk involved in producing the part, what we call producibility. So here they don't have a huge size variation they have. Now in this case here, that you're pretty much saying this here, but if they start creeping to either one of these limits, they run a risk of non-compliance. And hopefully, and I have taught manufacturing engineers showing them this, is that these two here, you know, what we're doing here, I'm definitely giving them a lot more variability here in centering up the process. So either way, if they go to either of the limits, they got to be careful of non-compliancy. If they do shoot and start making holes at this upper limit here, as large, then they got to be careful that if they exceed it, there's nothing they can do to make the part compliant. It's a non-compliant part. So again, my manufacturing engineers, hopefully they're looking at this and making a decision based on process. I've had some equipment, the machines were brand new, and they might run it down near the MMC size so that if there's any issues, they can blow the hole open bigger. So in other words, it's based on, they might have a variety of different machines that are available. What machine is available based on probability of being compliant, that then pick the appropriate tool size to make sure they don't violate either of the limits. So again, it's back to, I've definitely given my manufacturing engineers more control of their destiny to do this. And hopefully they just don't blindly jump and grab this tool size here, because if they do blow the hole bigger, it's a paperweight. Hopefully they do it on process capability, just FYI.
Okay, Ed, I have one more question for you, and this has to do, it's related with the bolt standard slide. Is the bolt head width F assumed to be the same size as the same round contact face under the head?
So we're dealing with the bolt here. With this chart here, is that, so could you say that one more time then, Wendy?
Yes, it says, is the bolt head width F assumed to be the same size as the same round contact face under the head?
Oh, okay. So F here is actually controlling, you'll see it across the flats. So yeah, I guess here, in that case here, they are assuming that they are the same.
Okay, great. And I have one comment from someone. Sorry. I think the title of the allowable position tolerance is a little misleading. It should be called the total tolerance, including the position control feature.
Okay, I'm not too sure. where that's being referenced or what's.
He says, I'm referring to the column itself. Joe, you're unmuted if you want to talk.
Hello.
Yes.
Yeah, the column, the table before this
So
had the table where you calculated the total tolerance on. Is it before this, or there were two tables, one for one feature control, the other one for the other feature control with a 0 position tolerance, and the other one had a 15 position tolerance.
talk about this here.
Yes, the allowable position tolerance column is a little. I didn't get it until I figured, oh, you included the position tolerance is included in that, so it's the total tolerance.
Yeah. So you're right here. So this is, we're saying the allowable positional tolerance. In this case here, this is going to be based on taking what we are given. You know, if I'm looking at this one here, that we're automatically allowed, if the feature comes in its MMC size of 15,000, that's its allowable position that's stated in the feature control frame. And because we have the circle M, the additional tolerance modifier, then based on, it's depending upon what size they make the hole. So here, depending upon what size they make the hole, the circle M modifier allows me additional tolerances as the hole gets bigger. The difference between the MMC size and the produced hole, I get this additional tolerance that then is added to what we're originally allowed 15. Then it then gives me this new allowable, or the actual geometric tolerance based on the produced size of the hole. So yeah, we do call it allowable here. Maybe there might have been better words we could use up here. Did that help, or?
No, I did. Thanks.
Yeah, so this here is just showing you the additional tolerance, and that's what the M means. And that additional tolerance is based on what size does manufacturing actually makes the hole. Now, if I didn't have this M modifier here, there would be no additional tolerance, and no matter what size they made the hole, it always, manufacturing would only be allowed up to what was stated in the feature control frame, in this case, the 15,000s. So here we're just stepping through showing how to derive the additional tolerance and what the new geometric tolerance would be based on that given hole size. So, and you'll notice here that in this case here, the virtual condition, no matter, and all these will all be the same, the smallest hole. So if you were to take a hole produced at 0.288 minus the allowable tolerance, it will still derive the hole could not act any smaller than the virtual condition size or the inner boundary of 265. Good questions. Good questions.
Great. Does anyone have anything else? Any other questions? Okay, Ed, I don't see any other questions. So the next thing that we get to do is draw. I'm going to have Tammy come over and help. We had 3 people answer submit answers that were correct. So we're drawing our winner for this month, and it is Julia Nikolsky. And they are not on today, so we will email them and let them know that they won. All right. I'm going to wrap this up if there aren't any other questions. So I want to thank everybody for joining us today. We are taking a break from posting another challenge question for a little bit. Ed's in the middle of a very big project, and so we're gonna take a little hiatus, but we will be back to it. So keep your eyes peeled for the next challenge to come out. And thanks everyone for joining again, and have a great weekend.